This unit is called linear programming, and the linear part comes because all the mathematical functions are linear functions, and the programming part comes because there's a very well-defined, highly structured method for solving these problems. It does lend itself nicely to computer programming. But in fact, when this subject was first developed in the 40s, computers weren't really a thing yet. So it was called linear programming because of the structure of the solution, because there was a very precise algorithm for solving it, even though they did all the calculations by hand at that time. Let's see. So let me start off with an example. This is the type of problem that you can use linear programming to solve. Okay, as usual with these introductory problems, especially, it's a rather silly example. By the way, I'm using my notes for finite math. It would take me at least a week to go through all this with my finite math class, but I'm going to do it with you guys in one day. So strap in. Let's see. Suppose you're taking a dozen 10-year-olds out to see Ice Age 4. Okay, so you're going out to the movies with a bunch of kids, and you're going to need to provide them with 44 ounces of popcorn and 56 ounces of soda to get them through the whole movie. Okay, so they're going to be able to share the soda and the popcorn. And you look at the snack bar, and you see that they offer two snack packages. There's one called the Gulpalicious, which has 12 ounces of popcorn and 8 ounces of soda for $8. And then there's another one called the Slurpalicious, which offers 7 ounces of popcorn and 11 ounces of soda for $7. The question is, how many of each of the snack packs, of each of the snack combos should you buy in order to get the required amount of popcorn and soda at a minimum price, right? So you got a reasonable estimate of how much popcorn and soda the kids are going to need, and the question is, how many of each of the two snack packs should you buy to get that amount, but at a minimum cost? Okay. Now, first, I'm just going to talk about how you formulate the problem as a math problem, right? As a linear programming problem. So translating the English of the story into linear programming problem. The first step is probably to just clarify what the question is asking for. So in this case, what they're asking for is how many of each combo should you buy, right? That means there are going to be two variables, right? So we're going to have an x variable and a y variable, and we could say that the x is the number of Gulpalicious snack packs you buy, and the y is the number of Slurpalicious snack packs that you buy, right? And the variables correspond to what we're trying to figure out, right? So we're trying to figure out the value of x and y, which is the number of each pack. Okay, so just identified the variables. That's probably the most basic step in solving the problem. Okay, next. The next thing is to identify what it is you're trying to achieve, like what your objective is. And in fact, we use the expression objective function to describe the function that we use to describe the objective, unsurprisingly. So if you look this over carefully, you'll recall that our objective is to get the necessary popcorn and soda at a minimum price. We're trying to minimize our cost, right? And so how do you express the cost of all the popcorn and soda in terms of the two variables? That's straightforward. We know that the Gulpalicious cost, wrong number. This is it. Costs $8, and the Slurpalicious costs $7. So the total price is going to be 8x, 8 times the number of Gulpalicious packs, plus 7 times y, the number of Slurpalicious packs, right? So the total cost is 8x plus 7y, and we're trying to minimize that, right? So we include the word minimize as part of the, clarifying what the objective is. Okay, so this is the objective function and whether we specify whether we're maximizing or minimizing. Okay, so we've got the variables, we've got the objective function. The next thing is to list the constraints, that is, the conditions that need to be satisfied. Right? We can't, obviously we could minimize the cost just by buying nothing. We could we could set x equal to 0 and y equals 0 and we have nothing. But we have to satisfy the conditions. Let's see, let me scroll down a bit. So the conditions here, that we need 44 ounces of popcorn and 56 ounces of soda, right? So we have to have enough soda and popcorn to keep the kids happy for the duration of the movie, right? So we have to express the fact that the total number of ounces of popcorn is at least 44 and the total number of ounces of soda is at least 56, right? So then what we need to do is figure out that if we buy X Gulpalicious snack packs and Y Slurpalicious snack packs, how much popcorn and soda do we actually get? Okay, well, we were told the ingredients, right? We were told that the Gulpalicious has 12 ounces of popcorn and 8 ounces of soda. The Slurpalicious has 7 ounces of popcorn and 11 ounces of soda. So we can put those numbers together and we can say that the total amount of popcorn is going to be 12 times the number of Gulpalicious packs we get, plus 7 times the number of Slurpalicious packs we get, and that has to be at least 44. The total amount of soda, number of ounces of soda, is going to be 8x plus 11y for a similar reason. There's 8 ounces of soda in each Gulpalicious and 11 ounces of popcorn. No, I'm sorry, 11 ounces of soda in each Slurpalicious, right? And that has to be at least equal to 56. Notice that these are inequalities, so the constraints are always weak inequalities. Weak meaning that they're less than or equal to or greater than or equal to, right? And they're always, in these linear programming problems, the constraints are always expressed as weak inequalities. So, okay, we've got that. And then there's one other. Oh, by the way, I just mentioned that sometimes it's helpful to make a little table of ingredients. At least this is what I recommend to my finite students. So I sometimes recommend making a table where the two different items you can buy are the columns, and then we also have the total number of popcorn and soda required, and then the rows are the ingredients in the packs, right? So then, the Gulpalicious has 12 ounces of popcorn, 8 ounces of soda, the Slurpalicious 7 ounces of popcorn, 11 ounces of soda, and then you have the totals on the right, and this way each row in the table corresponds to one inequality, right? And the only thing you have to worry about is you do have to worry about getting the inequality in the correct direction. That is it going to be less than or equal to or greater than or equal to? In this case, the direction is because these numbers over here, these are minimum requirements, so you have to have at least that much. So that's why I chose greater than or equal to in this case. Okay. There is one other thing. It's just a common sense thing that we do have to make a note of because it is a requirement, which is that you can't buy a negative number of Slurpalicious and Gulpaliciouses, right? You can't. In other words, you can't manufacture a snack pack and sell it back to the snack bar, right? That's illegal. So X and Y have to be non-negative. And in fact, that's going to be the case in all the linear programming problems that we'll do. In general, they're real-world problems. The variables represent real-world quantities, so they cannot be negative, right? So X and Y will have to be greater than or equal to 0. And we have to include those as part of the set of formal constraints. Okay, so together we've got 4 inequalities that make up the constraints, and then of course we have the variables and the objective function, right? So this, in the first blue box here, this is the formulation of the linear programming problem, right? We've converted that paragraph of words about the Ice Age 4, taking kids to see Ice Age 4, we've translated into mathematics at this point. Right, so we got the variables, we got the objective function, and we've got the system of constraints, right? Because we have this is the system of constraints. It's a system in the sense that all the constraints have to be satisfied simultaneously by the variables, right? So we have to find variables x or values for the variables x and y that satisfy all the constraints, and then among all those which satisfy all possible values that satisfy the constraints, we want to pick out the particular values of x and y that minimize this objective function. Now, for our purposes, we're going to want to think about this in terms of linear algebra. In particular, we can formulate this in the language of matrices. So here's what we'll do. We will think of the variables x and y as being a matrix, or rather a column vector of variables, right? So capital X will be the vector little x little y, and then we can also think. Let's see. We can also express the objective function 8x plus 7y. That has the form of a dot product, right? It's like we took the vector xy and we dotted it times the vector 8, 7. So, so I'm going to call the vector 8, 7, I'll call that b. That's also a column vector. And the objective function is b dot x, right? It's a dot product. And of course, we're trying to minimize that, right? Another condition here is that the variables have to be non-negative. So this is kind of an abusive notation. We're saying that the vector x has to be greater than or equal to 0. So we interpret that as meaning that every entry in x has to be greater than or equal to 0. Okay? Maybe I should have made this a boldface 0, but I think that's not usually done in the literature, so I just left it like this. But so we interpret this as meaning that every entry in x has to be greater than or equal to 0. And then finally, if you look at this expression down here, this seems like the result of matrix multiplication. It's like we've multiplied the matrix 12, 7, 8, 11 times the column vector xy. So we define A to be the matrix 12, 7, 8, 11. And then we want to say that A times x, which is this guy, A times x is greater than or equal to these constants, and so again we just define a new vector c to be 44, 56, and then the other constraint here is that A times x has to be greater than or equal to c. And again, we interpret that as meaning that every entry in A times x has to be greater than or equal to the corresponding entry in c. Okay, so in this case, A times x and c, they're both vectors. So the inequality says that the corresponding entries have to obey that inequality, right? The left side has to be greater than or equal to the right side. Okay, so in other words, by the use of matrix algebra, we can express this very, very compactly, right? We just say we're trying to minimize this dot product subject to the constraints that x is greater than or equal to 0 and A times x is greater than or equal to c, right? So as a matrix problem, it's completely equivalent, of course, but it's just a lot shorter. It's it's much simpler to work with if you think of it in matrix terms. Okay, so that is how you formulate a problem. Now I'm mostly going to be working with this matrix formulation over here, right? So that's what we're going to be working with. Although some of the examples I do will be two variable problems, and when you're just doing a problem in two variables, it's perfectly simple to just work it out without matrix algebra and just solving systems of two linear equations in two variables. That's perfectly easy to do, which is what we do with our finite students, and you can do that too when we're doing a two variable problem. When we're doing a bigger problem, then we have to, it does pay to use the matrix language, right? The matrix formulation when you're doing a bigger problem, because, no matter how big the problem is, no matter how many variables you got, the matrix problem always looks pretty much the same, right? It's always minimize b dot x given x is greater than or equal to 0 and A times x is greater than or equal to c. You just have to define what these constants are, right? But then the same basic scheme works for any size problem, right? So, and I'll show you how to actually solve these problems on using a spreadsheet. So I'll get to that later. And a spreadsheet is more or less uses the matrix formulation, right? So definitely become comfortable. Force yourself to become comfortable with this matrix language for describing these problems. Now here's another example I do in finite. I don't think I'm going to do it with you, but it's in the slides, it's in the notes, so you can look at it. But it's a somewhat confusing problem about ordering chalk for use at a college, and again the problem is simply to take this story problem here and formulate it as a linear programming problem. So I went through it here. You can look it over and make sure you get the same formulation that I did, or at least an equivalent formulation. Depending on how you define the variables, you can get slightly different formulations. So, for example, instead of defining x to be the number of pieces of soft chalk and y the number of pieces of hard chalk, I could have used different units. I could have said x is the number of boxes or the number of gross. A gross is a dozen. Right, 144 pieces. So there are different ways you can formulate this that would look different, but it should be equivalent. So when you've successfully formulated a problem, what you've got is, as I said, you've got three parts in the formulation. You've got the variables. You've got the not a good choice of color. You've got the variables, you've got the objective function, and then you have a system of constraints. And the most complicated of these parts, of course, is the system of constraints. You can have a number of constraints, right? And trying to solve all the constraints simultaneously can be tricky. That's what makes the whole problem tricky, right? You're trying to solve all of these constraints simultaneously with the same xy value. So the first part of actually solving this problem, right? Now that we've formulated it, we can think about actually trying to solve it. And the first thing to do is to wrap your head around this system of constraints. So one way to do this, actually a particularly good way to do it when you only have two variables, is to graph it. Because if you only have two variables, it's relatively straightforward to graph. It's very easy to visualize what's going on. So we're just going to graph each inequality on the same graph and find the so-called feasible set. The feasible set is the set of x and y values that satisfy all the constraints simultaneously. Okay, so here's a simple example. Now you probably did graphing inequalities back in high school. I'll just briefly review it. But if you have an inequality like, for example, x plus 2y is less than or equal to 4, then graphing it means shading all the points in the xy plane where that inequality is satisfied, right? All the xy coordinate pairs where x plus 2y is in fact less than or equal to 4. Well, to start off with, what we do is we graph the equation x plus 2y equals 4. Because, of course, that's going to be part of the inequality. That's going to be part of the graph of the inequality, right? Because it's a weak inequality. Inequality is included. So first we graph the line. Okay, so here's the line. I graphed it. I don't remember. Maybe I used MATLAB or Maxima, I think, on Linux. Anyway, so here's the graph of the line x plus 2y equals 4. It's the blue line. And then really the only thing that remains is which side of the line also gets shaded, right? If the line is where x plus 2y is equal 4, then it's pretty obvious, I'd say, pretty intuitive that one side or the other of this line is going to be the region where x plus 2y is less than 4, and the other one is going to be the region where x plus 2y is greater than 4. So we want to figure out which is which and shade the one that we want. So, okay. There's various ways to do this. Let me skip over this. The two main ways to do this are to First of all, you can just plot a test point. So for example, you take any point, like here I happen to look at the point 2, 3. So if you take the point 2, 3 and let's see, determine, oh yeah, just check whether it satisfies the inequality, right? Remember the inequality, going back to the top here, the inequality was this. This was the inequality we had to satisfy. If you plug in x equals 2 and y equals 3, sorry, x equals 2 and y equals 3 here, then you're going to get 2 plus 6, that's 10, and that is not less than or equal to 4. So therefore this point 2, 3, which is up here, right? Here's the point 2, 3, does not satisfy the inequality, so this point is on the wrong side, right? We want the points that do satisfy the inequality, so simply checking a single test point is enough to determine which side is the one we want and which side isn't, right? In this case, we want the other side, right? So that's how we know that we want to shade this side of the line. Okay, so the test point method is one way to determine which side to shade. Oh, by the way, frequently, in fact, usually, the easiest test point to check is 0, 0, right? That's a nice, easy test point because it's always easy to plug in, right? So for example, suppose we had, suppose, I keep forgetting to switch back to my pen. Suppose we had tested the point 0, 0. And recall the inequality was x plus 2y is less than or equal to 4. Well, if we plug this in, we get 0 plus 2 times 0 is less than or equal to 4. Well, that's true, right? That's true. And therefore, this point is on the correct side. And again, that would tell us that this is the side we want to shade. We want to shade the side of the line which contains the point that passed the test. Okay, so that's one way to do it, the test point method. Another way to do it, though, is you could just actually satisfy the inequality for one of the variables. Solve the inequality for one of the variables. So what you could do is, here's the original inequality. We could solve for x, for example. X is less than or equal to 4 minus 2y. Now, this actually gives us the solution because we know that when x is equal to 4 minus 2y, then we're on that line. Right, so this line here, this is the line where x equals 4 minus 2y. So where is the region where x is less than 4 minus 2y? Well, that would be the region to the left, because x gets smaller as you move to the left, and it gets bigger as you move to the right. So on the left side of that line, that's the region we want to shade. Right? So we get the same answer we got before, right? You could also have solved for y, and then you would have found that, like, for example, if I solve for y here, x plus 2y is less than or equal to 4. 2y is less than or equal to 4 minus x. Divide by 2. Remember, though, that when you multiply or divide by a negative number, you have to change the direction of the inequality. That wasn't necessary here because we were dividing by 2. So okay, so now we've got this. We know that y is less than or equal to 2 minus x over 2. Again, the line is where y is equal to 2 minus x over 2. So where is the region where y is less than 2 minus x over 2? That would be below the line, right? So however you want to think of it, if you solve for x, you can think of it as to the left of the line. If you solve for y, you can think of it as taking the region below the line, but either way you get the same region. Okay? And so that's how you graph an inequality. Now, the extra difficulty is that we have to graph several inequalities at once. Okay, so here's an example graphing a system of inequalities, right? We've got these two inequalities, the same one as before, x plus 2y is less than or equal to 4, but a new one, y is less than or equal to 7 minus 3x. So, the idea is to graph them both on the same plane, and then find the intersection of the two, find the region where the shaded, where each inequality overlaps, right? The shaded region for each graph overlaps. So okay, so quickly we could graph the second one, since we already did the first one. The second one, let's see, y equals 7 minus 3x. That's actually in slope-intercept form, so we can tell the slope is negative 3 and the y-intercept is 7. So that is what the second inequality looks like. And again, we can use the test point as a, I'm sorry, 0, 0 as our test point, and that's nice and simple. So if we take that, where was our, oh, I forgot where the objective function, oh, it was this guy, right? So the objective function was this, and if we plug in 0, 0, as we saw, this is true, right? So, so we can use the same test point for here that we, 0, 0 for here as we used before, and it makes the inequality true. So once again, that tells us that we want to shade the side that contains the test point, right? We want to shade the lower left side of the line. Oh, incidentally, the only restriction on the test point is it has to be off the line that you're working on, right? You don't want to pick a point that's on the same line that you're working on, because we already know that on that line the two sides are equal, right? And so that won't be a good test point. We want to pick a test point where it's either less than or greater than, so we can determine whether the inequality is true or false. Okay. So here's the graph of the second inequality. If we put them together, we get this, and the overlapping region is down here. Let me see if I can shade that a little bit. So here's the overlapping region down here. So far, our feasible set is that overlapping region down here. It actually goes on forever, right, in principle. However, there are two more inequalities to take into account, two more constraints. Remember that we had the natural constraints. Oh, by the way, here I'm just showing you another way to think about it. You can think of forming the intersection of two sets. You can also, instead of thinking of it as forming the intersection of two sets, you can think of it as excluding both regions. So one constraint excludes one region. So for example, the blue constraint, the first constraint, excluded everything above it, everything up here, and the second constraint excluded everything also above it over here. And if you put the two excluded regions together, then you get pretty much the same answer, just in a slightly different way. Just a slightly different way to think about it. Okay, now, in addition, however, to the two constraints we got, we normally, well, I'm sorry, the two constraints we just considered, normally in one of these linear programming problems, you will also have the natural constraints. So you also have constraints that tell you that the variables have to be non-negative. So x is greater than or equal to 0 and y is greater than or equal to 0. Fortunately, they're real easy, because the line x equals 0, that's the y-axis, right? So the y-axis is this line, x equals 0, and the line y equals 0 is the x-axis, and that's the line y equals 0. And clearly, x is greater than or equal to 0 to the right of the x-axis, sorry, the y-axis, to the right of the y-axis. I will get this straight. And y is greater than or equal to 0 above the x-axis, right, above the line where y equals 0. So when the upshot is that if you have the two natural constraints, it means that you're restricted to the first quadrant. So you can cut off your feasible set at the x and y axis, because you have to be in the first quadrant. Okay, so putting this all together, if we had a problem in which these were the four constraints, right? So these were the four constraints. We have two natural constraints, and then two particular constraints for whatever the story problem was. Then the feasible set would look like this. It would actually be a quadrilateral region, right? And it's got four corners and four sides, right? So the four corners and four sides. Now, it is possible to have an unbounded feasible set, that is, a feasible set that goes on forever. This one is bounded because it's just a finite quadrilateral. But it is possible that you could have a feasible that's open on one side or open in one direction, right, and goes on forever. That's certainly possible. We'll talk more about that later. But for the moment, there's one other important thing you have to do, which is challenging for finite students. I don't think it will be challenging for you. You have to be able to determine the corners of the feasible set, right? However many corners there are, it's important that you be able to calculate the coordinates for the corners. So, the way you do that is by solving systems of equations. So for example, well, first of all, there's obviously an easy one here. A is obviously the point 0, 0, right? B and D are also pretty simple because B and D are just the intercepts of the two lines we already considered earlier, right? So D, for example, is the intercept of the first line. So this line here was the line was at x plus 2y equals 4. So D is the y-intercept of that line. So that's pretty easy to figure out. And in a similar way, B is the x-intercept of the other line. Oh, what was the other line? It was y equals, oh, I forgot already. What was it? 7 minus 3x. Okay. Where did I go? I'm lost. Okay, there we go. Y equals 7 minus 3x. Okay, so those are pretty easy to get because of the intercepts. Now, the only one that's a little bit difficult is C. C is where those two lines, from the first and second inequality, that's where those two lines intersect. So you have to solve a system to figure that out. Right? So to find C, right? C is formed where these two lines intersect. So we have to solve the system of these two equations, right? Well, okay, that's not hard to do. In fact, in this case, it's kind of begging you to just use substitution. Just plug 7 minus 3x in for y in the first equation. So ultimately, we figured this out, and what did it turn out to be? That 1. So x was 2 and y was 1. Okay. So ultimately, you're able to pretty easily figure out the four intercepts, right? Of course, there could be the four corner points, rather, the four corner points of the feasible set. There could be any number of corner points. There could even be none, I suppose, if there's only one constraint. No, that's not really possible. There's always got to be at least one constraint because of the natural constraints. There's always got to be at least two constraints because of the natural constraints. But there could be any number of corners, right? It's important that you determine the values of all of them. I'm a big fan of tech. You might even call me a junkie. There are some online tools. You've probably seen them, right? I think you've used, if you're in secondary math ed, you've probably used Geometer Sketchpad. And there's some similar apps for graphing linear equations and linear inequalities. So let me just show you how you can do this more easily. You don't have to do it by hand, and you can check your answers. Now, of course, if you're a secondary math, if you're going to be a secondary math ed instructor, you really ought to be quite comfortable solving systems of linear equations in two variables. But nevertheless, it does get tedious. So I'm going to show you my favorite tool, which is GeoGebra, and another popular one is Desmos. So let me just do this quickly. GeoGebra, it's like algebra, except it begins with GEO instead of ALG, GeoGebra. Okay. And you can start the calculator, and then what you can do is over here, you can just type in the inequality you want to graph. So x plus 2y is less than, so I'm typing the less than, and then the equals key, and it turns it into less than or equals 4. There we go. That's nice. And another one would be, what was the second one? Y is less than or equal to 7 minus 3x, right? Okay, so there you go. And if you want to expand it, you can you just use the scroll wheel to blow it up. And you'll notice that this is nice. In fact, we can even read off the corners, right? So this corner is at 1, 2, which is what we got earlier. This point here, this is another corner, was actually one of the intercepts, is at 0, 2, and then 0.00, 0, and then this point is about 2.3, I'm not sure, 2.34 or something, right? That was the one that wasn't a whole number, 2.3 something 0. I didn't bother to graph the natural inequalities because those are just the x and y axes. You can just see them without graphing them, right? Not really necessary. So okay, so I recommend this as a way of checking your work or just simplifying some tedious calculations that you have to do. So if you have to do like 3 or 4 inequalities, it can be a real pain in the neck, and it's easy to make a careless error. So feel free to use this. The other one that's popular is Desmos. Desmos, it's beautiful free math. Yeah. That's a nice slogan, yeah. Let's see, so, let's go to the graphing calculator. And yeah, I think it works almost exactly the same way. I'm not quite sure what the differences are between them, but for our purposes, they seem to be almost identical. X plus 2y is less than or equal to 4, and then y is less than or equal to 7 minus 3x. Yeah, there we go. And yeah, I can just use the scroll wheel to zoom in. And yeah, it makes it real easy to read off the corners, right? So yeah, so feel free to use these tools. Okay, having formulated the problem and then graphed the constraints, we are finally ready to actually get a solution. So the feasible set that we graphed. So here's the example from the the example that we graphed earlier, not the story problem about the popcorn and soda, but just the graphing example. We ended up with this feasible set here, right? 4-sided feasible set, and those are that's the set of points that satisfy all the constraints, right? Whatever the physical constraints were in the original story problem, these are the points that satisfy all those conditions. And of those points, we're supposed to pick out the one point that has the best value for the objective function. Okay, well, suppose hypothetically, in this example, suppose the objective was to maximize the value of 3x plus 2y. Now remember, we can think of the objective function as a dot product. We can think of it as b times x, where in this case, b would be 3, 2. b would be the vector 3, 2. So in this diagram, I've actually drawn the vector 3, 2. So that's this guy. This is the vector 3, 2. And when you take a dot product, you know, you're kind of finding out to what extent does the vector x align or point in the same direction as the vector 3, 2, right? The dot product, remember, it involves the cosine of the angle between them. So the more their directions align, the greater the dot product will be. So in brief, forming the dot product, you know, x dot or b dot x, you're trying to find the vector x in the feasible set which points the farthest in the direction indicated by b. Okay? So, well, if you think about that, the direction indicated by b, well, you know, b is a vector, so there's the direction indicated by b. Which point in the feasible set points the furthest in that direction? Well, that would be the point in the feasible set which, when projected onto that vector, goes the farthest in that direction, or has the largest projection onto that vector. So I drew a couple of examples. So for example, here's a point in the feasible set. Let me try a different color. How about blue? Maybe light blue, maybe that'll work. Yeah. So there's a point in the feasible set, right? Well, actually, I could have taken any point along this line. Any point along this line. those are 3 points in the feasible set. When you project them onto the vector B, they all project onto this same point here, right? But that's not as big a projection, that's not as long a projection as you can get by picking, for example, if you pick a point out here and project that onto the vector B, you get a longer result, a greater result. And the maximum result you can get is by going to the edge of the feasible set right here, this corner, and when you project that, you get this. The orange lines here are basically lines that are perpendicular to the objective vector B, and all the points in those orange lines have the same projection, so they basically all have equal objective values, right? They all produce the same value for the objective function. We want to pick a point that corresponds to the orange line that's farthest out in the direction of the objective vector. So that's always going to be one of the corners of the feasible set, right? If you're looking for an extreme point, right, the point that has the greatest projection onto the objective vector, you're always going to want to pick one of the corners, right? The corner is always going to be one of the extreme values because it's an extreme point of the feasible set. Similarly, if you wanted to minimize this quantity, like we were talking about maximizing it, but suppose you wanted to minimize the quantity of 3x plus 2y, it would be very similar, except that you'd want this point here, right? So you'd want to pick the vector that has the smallest dot product, right? And that would be 0, 0. Right? So if you're looking to maximize, then you want to pick the vector that, or the point x that points furthest in the direction of the objective vector. And if you want to minimize the value of the objective function, then you pick an x value that minimizes the value of the projection or the value of the dot product, right? So there's a nice, simple geometric interpretation to this, right? So once you get the hang of it, you can actually spot the solution immediately as soon as you've identified what the objective vector is, like in this case it was 3, 2, and you've got the feasible set, then you can immediately pick out which point is going to give you your max or your min. Right? Just to take another example, so suppose we have the same feasible set as before, but now the objective vector is different. Suppose the objective function is x minus y. In that case, the objective vector b would be 1 minus 1. So here's 1 minus 1 over here. Right? I've sketched that. And now we can see that if we're trying to maximize, we want to use this orange line. And that means that this corner of the feasible set will be the point that maximizes the objective function, whereas this corner of the feasible set will be the point that minimizes the value of the objective function, because that's the one that points farthest opposite to the direction of the objective vector. Okay, so it's pretty simple to pick those out, especially when you're dealing with a bounded feasible set. So remember, this feasible set is bounded, and it's just a finite set. Well, that is, it has finite extent, right? It doesn't go on forever in any direction. But one other thing we should talk about is what about unbounded feasible sets, right? So this is possible. So here's an example. So here's a feasible set down here. Oh, by the way, here are the constraints up here. Let's see. Yeah, these are the constraints. So we have the natural constraints, and we also have two other constraints. X minus 2y is greater than or equal to negative 6, and x minus 3y is less than or equal to negative 2. And I've graphed it down here, and actually this, of course, I can only graph a finite amount of it, but this one actually goes on forever to the upper right? It extends forever to the upper right. So this is an unbounded feasible set. It actually goes on forever in one direction. Now, of course, as you might imagine, the thing about unbounded feasible set is there might not be an optimal value. There might not be a max or a min. So, for example, suppose that we're trying to find the, let's say the max, let's just start with the max of 3x plus 2y, right? So if the objective function is 3x plus 2y, that means our vector b is 3, 2. And here I've graphed the vector 3, 2. Right? So it points that way. Now, which point in the blue feasible set goes farthest in the direction of the objective vector? Well, you can see there's no answer to that question, because you can get points that go farther and farther in that direction as you go farther out in the feasible set. So pretty clearly there is no one solution to this problem. There is no point that's an actual maximum. So in this case, we would say that there is no solution to the maximum problem, right? There is no maximum of 3x plus 2y on the given constraints. However, if you were looking for the minimum, well, that you could do, right? You can find the minimum, because the minimum, for the minimum, you're going to want to find the point in the blue feasible set that extends farthest in the opposite direction to the objective vector, and that would be this point. So once again, it would be 0, 0, 0. Let me just caution you that it isn't necessarily the case that when you have an unbounded feasible set that there will be no maximum, but there will be a minimum. It actually depends on the precise nature of the objective function. So as an example, suppose your objective function is y minus x, right? So y minus x, that has corresponds to a vector b equal to negative 1, 1, right? The coefficient of x is negative 1, coefficient of y is 1. And so I've graphed that over here. Negative 1, 1 points that way. And now, if you're looking at the same unbounded feasible set, you can see that there's a maximum over here corresponding to this point, right? But there's no minimum, because in fact this feasible set can go infinitely far out in the opposite direction to the objective vector, right? So you can keep going as far as you want in the opposite direction, and there'll still be points in the feasible set that line up with it. So you can actually get so this is a case where there will be no minimum, but there is a maximum, right? So if you throw in some negative signs into the objective function, then that can alter whether it's the max or the min exists, and it's possible that they could both exist, or they could neither exist, or one without the other. So anything is actually possible depending on the precise nature of the objective function and the way it interacts with the feasible set.